Yeah. So hello everyone. I'm Han Li. I'm from University of Munich. I study computer science, so this talk might be a little bit different from what you mostly see, but I think it will be interesting. So I collaborated with Professor Volker Trask, who is also here today, and this is also done with Jindong Wu, Radha Kona, and Zahan Sharif. Okay. Yeah. So we all know that language is a major means of communication. So to agents like humans, we communicate through language. Then how can we make sure that the agents understand each other? For example, if the first agent says that it's a cat or dog, how do we make sure that the second agent has the same understanding of what the first agent says? So in this work, we run experiments using artificial neural networks, so the deep learning models. Here is an example. So first, this is an input image from the real world. The first agent is a blip model. It's an image to text model. So it can give an image, it produce a text description for that image. And this is the trained model. So we use it to describe the input image. And this is the first agent. And then it says there's a yellow and black bird on tree branch. And we have the second agent, the stable diffusion. Then the question is, how do we make sure that the second agent, the stable diffusion, understand what the blip model says? So if the yellow bird refers to the same thing for both models, so we propose that to use this stable diffusion model, the second agent, to generate another image. So this is like the mental imaging. So if you heard a sentence, you picture it in your brain. Of course, we don't reconstruct the image to the pixel level, but in our experiment, in this simulation, we use the deep learning models and use it to generate an image from the sentence. So to simulate this process. And we claim that if the generated image is close to the input image, then the two models understand each other.
So close in what sense?
Sorry?
Like close in terms of the precise?
Yeah, that's a good question. So first of all, we don't use the mean squared error because that's not a valid solution. Instead, we extract the embeddings for the image using image encoder. And in our experiment, we tried different image encoders, either trained only on the image data or trained using cross modality data, and we find the same conclusion. Yeah. Yes. So we can say that. So as a result, if the reconstructed image is close to the input, so both models understand each other, and as a result, we can say that the description is more accurate and has high quality, contains more information to the input image. For example, the upper one is a better one than the lower description, and you can say because the reconstructed image is different from the input image compared to the first one. Yeah, so that's the basic motivation. Yeah. So technically, we use image to text models, Flamingo and Blip. Flamingo is from DeepMind. So it has an image encoder and has a language decoder. The language decoder is a GPT model. Probably think all of you know that. And the text-to-image model is from OpenAI. It's a DALL-E model. And also we have used this stable diffusion. Okay, so here's the pipeline. Given an input image, we generate 10 captions from the Blip model. And then for each generated caption, we generate a new image. Then we compare the similarity between the generated image and the input image. And we evaluated the quality of the generated caption using human labels. So we assume that the human description are the most accurate, or so the golden truth for the input image. And this is the result. So on the x-axis, so shows that so the further from the origin means the more different of the generation, and the y-axis shows the quality of the caption. So you can see this trend, and it's consistent to different metrics, like the similarity metrics and the caption metrics. And so the conclusion is that the quality of caption can be evaluated by assessing the image reconstruction produced by a text-to-image model. The best text for image is the one that leads to the most accurate reconstruction. Yeah, so this is the first part of the experiment. We use pre-trained models and we don't fine-tune them. So it's like we select the best one, the best pairs that has the minimal misunderstanding. And now we would like to improve a specific model. So we take one image to text model and one text to image model, and we let them involve in this task, and we fine-tune them. So on the left side, so the Blip model receives the input as image and the output text. And then this generated text is fed to the Stable Diffusion model. So, and we, based on the reconstruction quality, there's another cost function that can optimize the Blip model. So the Blip is not only produce captions that are close to the labels, but also that can lead to good reconstruction. Yeah, so yeah, you can see that we improved the result. So in summary, that so the idea of our work is that by encouraging the mutual understanding of both models, we are able to improve them. So either in the fine-tuning setting, the inference setting, and also in the in the training-free setting, and also in the fine-tuning setting. And we also like the idea in our work is connected to embodied cognition. So when we so it's like the discrete symbols are perceived like in our brain as low-level features. So we have this back propagation. So when we try to understand a symbol, we do back propagation and reconstruct low-level signals. Yeah. Okay, so that's the talk. Thank you.